Hi everyone, my name is Erika Sweet. I use she, her pronouns. I work on Microsoft's C++ team, and this is cross-platform pitfalls and how to avoid them. If you have any questions about this talk or any other talks that folks on my team are giving, or have comments, feedback, or just want to say hi, then please stop by our table at the virtual expo hall. Tooling for C++ cross-platform developers is a fractured solution space. And to help illustrate this point, I'm going to start with an example rooted in combinatorics. So let's say that I'm a C++ developer working on an application that needs to run on both Windows and Linux. So I want to choose one cross-platform build system generator out of 10. I want to choose 2 package management solutions out of 6. Because I think I want to use the system package manager on Linux, which means I'll need to figure something else out on Windows. I want to choose 2 IDEs or editors out of 8. Maybe folks on my team have different preferences, or maybe I'm opting for platform-specific solutions. I want to choose 1 cross-platform unit testing framework out of 10. And I want to choose 1 continuous integration system out of 4. And obviously this is just an example with arbitrary coefficients and restraints that I've imposed, but already we're up to 168,000 unique combinations of tools that I can choose from. As a cross-platform developer who uses these tools, this gives you a lot of flexibility, but it can also make your life harder. It can be difficult to get started because there's simultaneously too much documentation that you need to sift through and no authoritative source of truth on the workflow that you're actually trying to accomplish. It can make it harder to find and leverage the work of others. And generally, it makes it difficult to push the field towards a consensus of good practice. As someone who creates or contributes to these tools, it can also be frustrating because the overwhelming amount of options makes it difficult for any one tool to acquire the critical mass necessary to achieve a positive feedback loop. And I don't have all the answers, and I understand that your team's needs and matrix of solutions might be entirely unique. But as a part of my job, I do talk to cross-platform developers to better understand their workflows, their pain points, and the tools that they're using or want to use to help address those pain points. In this talk, I'm going to synthesize some of the common problems and pitfalls that I hear real teams facing and offer commentary on the solution space rooted in widely adopted tooling. So I've split this talk into 4 sections or stages in a development workflow, starting with build systems and build system generators, dependency management, debugging, and testing. I'll also be showing 2 demos that showcase some of the tooling my team has been working on in the past year, like vcpkg and Visual Studio's CMake support. But if you're not using vcpkg or Visual Studio or Visual Studio Code or anything at all in the Microsoft ecosystem, then I hope you will still find value in this talk because the problems and tools that I'll be discussing, whether it's a unit testing framework or a build system generator, are transferable and not tied to just one IDE. So with that, I'll dive into the first section on build systems and build system generators. For every other section, I'm going to start by synthesizing some common problems and then offer commentary on the solution space. But for this section, I flipped it. So I'm going to start by giving an overview of the solutions and then talk about the problems that are specific to one solution. Let's start by differentiating between build systems and build system generators. So a build system we can define as a tool or set of tools used to compile and link source code. And oftentimes these build systems will only run on a subset of operating systems. Popular examples include all the different flavors of Make, as well as build systems that are tied to an IDE, like Xcode or MS Build. To help address the problem of platform-specific build systems, we have build system generators, which are used to generate project files for specified build systems and can be used to maintain one build script or one source of truth when targeting multiple platforms. And whether you love it or hate it, CMake leads the market as a cross-platform build system generator, which leads to something called the CMake network effect, which is basically the idea that other projects, libraries, and tools are more likely to be using CMake and integrate nicely with your own CMake projects. We've also seen more and more editors and IDEs adding their own CMake support in a response to this effect. But even if you're using CMake or you know that you want to use CMake, there's still a lot of ways that your life can be difficult, and that's what we're going to talk about next. CMake and the problems. One thing that I hear repeatedly from cross-platform developers is that it can be difficult to learn the language of the build system. This might be especially true if you're used to an IDE that helps to manage the underlying build system for you, like Visual Studio and MS Build. Relatively common actions, like adding a new source file to a project, need to be accessible to everyone, devs, testers, and not just your build architects, who are your in-house CMake experts. But with really complicated build scripts, even adding a new source file to a project can become a non-trivial task. Lastly, just like C++, CMake is its own language, so it's yet another set of best practices in syntax that you'll need to become familiar with. Another pitfall is not abdicating as much responsibility to CMake as you can. CMake itself is cross-platform, and it has a lot of primitives built in to help abstract away platform and compiler specifics. But you can make your life harder by trying to fight with CMake and re-implement that functionality on your own. So I've identified a few examples and recommendations to better illustrate what I mean by this point. First is to use built-in CMake command line tools instead of calling system commands directly. So CMake has a lot of abstractions for common system commands like make directory, remove, copy, echo, and you can call them instead of wrapping your system commands in platform-specific logic. This create symlink command that I'm using in the example was added to CMake in CMake 3.13, and all of these commands can also be used when you're invoking CMake from the command line. This is just an example of what it might look like in the context of a CMake script. A second example is to use built-in project commands whenever possible, instead of re-implementing functionality with custom functions and compiler-specific logic. So this command, target precompile headers, was recently added to CMake in CMake 3.16. Before that, you might have had to hand roll your own function with compiler-specific logic, or you might have used Conan, which stands for Compile Time Reducer, and was an open source CMake module that's now fully integrated into CMake. But Conan was over 1,000 lines of CMake that's now abstracted for you in a single command. All that you need to do is pass a list of public, private, and interface headers to CMake on a per target basis. You can also reuse precompiled header artifacts from other targets instead of always generating your own by using the reuse from option. Lastly, you don't need to modify your C and C++ source code at all to use this command because precompiled headers are force included in all compilation units. A third example is to set compile features. So in this first example, we're setting one compile feature that's required to compile this specific target, or meta features. So in the second example, we're setting a C++ language standard that's required to compile this target, instead of manually setting flags. You don't need to be in the business of maintaining flags and error messages for every version of every compiler, because that's something that CMake can help you with. You can also set optional compile features that say, hey, use this feature if it's available, but don't set a hard requirement, or conditional compile features. So for example, you can use a generator expression to say, require this one specific compile feature only when the compile ID matches GNU. A fourth example is to keep your paths platform independent and not platform specific. So in this example, there's a few things going on here. The relative path include my target for the install interface is being interpreted relative to the installation prefix. The variable CMake current source dir is going to evaluate to the source directory that's currently being processed. So in general, use relative paths, and in that same vein, if you're searching for tools, you can assume that the tool binaries are on path and fail otherwise to avoid searching in platform-specific directories. Another recommendation is to avoid backslashes. So you can use the file command with the two CMake path or two native path options to convert native paths and system search paths to and from CMake style paths with forward slashes. And lastly, cross-compilation with CMake can be pretty straightforward, but a lot of folks tend to over-configure their toolchain files. So the recommendation is to use one toolchain file per target platform and avoid adding logic to your toolchain file. This example that I have here is one of the most simple toolchain files that you can author, but it still gets the job done. All I'm doing is setting my target system and architecture and then picking my compilers. This was just a few examples of some cross-platform specific gotchas that you can run into when you're authoring your CMake scripts. But there's a lot of other ways that modern CMake can make your life easier. And so for more information, I would recommend these two resources. The first is a recording of a conference talk, and the second is some documentation published by Gitbook. All right, on to the second section, which is dependency management. And this time I'm going to start with the problems. Dependency management is a pain point for all C++ developers, unless you're part of the lucky 14.9% who say that it's not a significant issue for me. But there's a couple of problems that might be exacerbated for cross-platform developers. If you are building a library from source by following the instructions in the repository's README, then you're going to need to follow those instructions, as well as manually fetch and resolve all transitive dependencies, including building and installing the right version of the dependency to not break your dependency tree on all the different platforms that you're working on. You're also going to need to maintain multiple sources of your dependency tree across all the different platforms. I was talking to some developers who were working on Windows and trying out WSL, or the Windows subsystem for Linux, and they were lamenting on how nice it would be if they were able to leverage all the work that they had already put in to configure their dependency tree on Windows when they're working on WSL. And lastly, whatever tool or solution you use to manage your dependencies, it would be nice if that solution itself was cross-platform so that you can use the same workflow across multiple platforms. And again, there are a lot of solutions in this space already. System package managers can be really nice for installing tooling, but they can make your life difficult when you're trying to install packages. They oftentimes don't have the most up-to-date version of a package, and they can also silently update things from underneath you with no warning. So for example, you might pull in a new dependency that updates the version of several dependencies downstream in its own dependency tree. They're also system-wide and not project-specific, which can make it nearly impossible to work on two incompatible projects on the same system. And lastly, they are platform-specific and oftentimes even distro-specific. So apt is really popular, but it only works on Debian-based Linux systems. A second class of dependency management solutions is build system-specific package managers. And the primary example that I'm thinking of here is NuGet. NuGet is not a recommendation for cross-platform development or for any C++ development. NuGet does do some nice things, like it has some build system integration and IDE integration, and it provides a way to share pre-built binaries and sources. But at the end of the day, it's tied to the build system and not the language. So for example, NuGet also serves .NET developers who have an entirely different set of needs than C++ developers. Finally, there are language-specific package managers, which is our recommendation for C++ cross-platform development. Two C++ package managers that are being actively invested in are Conan and vcpkg, and this list of qualities applies to both of those tools. So both Conan and vcpkg are themselves cross-platform and allow you to bring down and build libraries from source on Windows, Linux, and Mac. They both automatically fetch and resolve transitive dependencies for you. With Conan, you can acquire pre-built binaries, and with both Conan and vcpkg, you can cache binaries to speed up the amount of time it takes to download and install libraries across multiple systems, and to ensure that every developer and your continuous integration system are using the same version of the library built the same way. Both Conan and vcpkg support some declarative manifest file where you can declaratively specify your dependencies one time and then check that file into source control. Conan and soon vcpkg will enable you to install libraries from multiple sources. So that means you can use the same tool to install your proprietary libraries, your own custom fork of an open source library, or an open source library. And finally, Conan and soon vcpkg support versioning, which is the ability to specify which specific version of one specific library that you want to install. vcpkg is the tool that my team works on, and binary caching and support for a declarative manifest file are both new and now available. And registry support, which is what vcpkg calls the ability to install libraries from multiple sources, and versioning support are both coming soon. It can be difficult to change your package management solution, especially if you're working with legacy code, but we do see that C++ package managers like vcpkg and Conan are on the rise. And with that, I'll jump on into my first demo. So here I have a CMake project open in Visual Studio. And the first thing I'm going to do is generate the cache. This is the same as calling CMake configure from the command line. So it generates the cache and writes the build files. I'm working with a fork of Box2D Lite, which is a more streamlined version of Box2D, the open source physics library. And I also have this folder open using Visual Studio's native support for CMake, which means that I'm opening this folder directly without ever generating Visual Studio project and solution files. So it looks like generation has finished, but with an error. I'm missing a dependency because CMake cannot find GLAD. So this repository is configured to use a vcpkg manifest file to acquire its dependencies. I'll open that up now. And because one, I'm using the vcpkg toolchain file, and two, I have this vcpkg.json file adjacent to my root CMake list in my project tree, then when CMake is called to configure the project, vcpkg will automatically bring down and build all of the dependencies that I've specified here from source, or download them from a binary cache if I'm using binary caching, and install them into a subdirectory of this project's output directory. So all I need to do to add the missing dependency is add GLAD to this list. And this file can be checked into source control with the rest of my source code. So now I'll save this file and try regenerating the cache again. And there's three things that I want to point out. One, you'll notice that I didn't specify which triplet of these dependencies I want to install, and that's because the vcpkg manifest file is integrated with Visual Studio such that the triplet that's built by default matches the active CMake configuration. So because an x86 Windows configuration is active right now, the x86 Windows triplet of all of these dependencies will be built by default. Another thing is that all the dependencies that I've specified are just strings, but I could also specify objects if I want to include any optional keys, like a platform expression that says which platforms are or are not supported by a specific dependency. And lastly, I want to underscore that I didn't need to make any changes to my build scripts to use this functionality, so you can bring your projects exactly as they are. All I needed to do was add this vcpkg.json file to the root and use the vcpkg toolchain file. So it looks like CMake generation has been done, and there's a few things that I want to point out. So one, you'll see that vcpkg is trying to build and install 6 packages, but I've only specified 4. And 2 have an asterisk by them, and that's because vcpkg is automatically fetching and resolving all of my transitive dependencies for me. You can also see that this operation took a suspiciously short amount of time, and that I'm attempting to fetch 6 packages from NuGet and restoring 6 packages. And that's because I'm using vcpkg binary caching. There's 2 different backends that you can use with binary caching. You can use a file share, or you can use NuGet, which essentially uploads binaries as raw NuGet packages, which allows you to use any binary hosting service that already supports NuGet. So for example, I'm using GitHub packages to host these binaries. And because of that, all of these installations are taking 104 milliseconds, all under a second here, and the entire operation took about 10 seconds. So now that cache generation is complete, I can build and run the samples executable on Windows. So this is just a demo application that was included with the static library. And here is samples. Now I'm going to switch gear a little bit and start making some edits to my CMake scripts. So I'll switch into CMake targets view, which is a more CMake-centric way of viewing my code organized by target. And I'm going to open the CMake list that defines the samples executable. One of the problems that I addressed earlier was learning the language of the build system. So one feature that we've added in the past year to help address this is language services for CMake. Just like when you're using or working with C and C++ source code, you can now right-click on a CMake variable and peek definition or go to definition. So here I'm seeing that sample source files variable defined for me. I can also right-click on a target and find all references. So this will list all the different times that this samples target is referenced in my entire project tree. And with really complicated source trees and build scripts, this functionality can be really helpful. Another feature that we've added in the past year to try and address this problem is project manipulation support. So now I'll pretend that I want to add a new test. So I'll open up the CMake list that defines my test executable, right-click on the executable, add new item. I'll add a new CPP file and I'll just call it new test.cpp. And now instead of just dropping that file on disk, Visual Studio is trying to understand where it might add a reference to this newly added source file. And if there's any ambiguity, then Visual Studio will prompt you with multiple options. So in this case, it's offering to add the reference straight to the add executable command, or it's also offering to add it to a set command. And because I'm using this test source files variable to define all of my source files, that is the only option that I would want. But I'm not actually going to make these changes, so I'll go ahead and cancel that. And now I'll hop back on over to the slides. All right, so we can quickly recap what we just covered in that demo. We showcased 2 new VC package features, a VC package manifest file where I declaratively specified my dependencies, and that file can be checked into source control and shared between my team. and vcpkg binary caching. I was using binary cache that was hosted in GitHub packages and downloading and installing those cached packages locally. We also showed 2 new CMake features. The first was CMake language features, where I can go to definition, peek definition, and find all references on CMake variables, targets, and functions. And we showed this on CMake variables and targets. We then showed CMake project manipulation support, which allows you to add, remove, and rename files and targets without ever modifying your build scripts by hand. And we showed the example of adding a new source file to a target. And with that, we can jump on into the third section on debugging. And again, I'm going to start with the problems. One thing that I hear repeatedly from customers is that they're unfamiliar with platform-specific tools. And this might be especially true if you added support for a second platform after your project already existed. So for example, you might work primarily on Windows and have relied on the Visual Studio debugger, but then you also added support for Linux. And a common theme that I hear in a response to this problem is that teams will have a few specified Linux devs who are comfortable using GDB from the command line and are responsible for debugging all Linux failures. And this can definitely help, but it doesn't really address the root of the problem. A second source of tension is if and when to use a graphical interface versus a command-driven interface when debugging. And command line tools are perfectly fine, but there might be some times when you or other folks on your team would prefer a graphical interface. Maybe it's to see breakpoints highlighted, or maybe it's to have both the watches and locals windows open simultaneously and staying in the same visual location as you step through your code, instead of having to request that information on each step or scroll up and down in your terminal. Command line tools can also have a greater learning curve, which again is perfectly fine, but if that learning curve only exists on one of your target platforms, then it might lead to some unbalanced solutions, like only a subset of your developers being able to debug all Linux failures. And lastly, we know that some developers will actually switch between platforms daily or weekly to work natively on that platform when debugging platform-specific issues. And this works, but it can also be really unproductive, especially if you're using a different editor or debugging tools on those platforms, because then you might need to reconfigure your project in all of those different contexts. Fortunately, there exist a lot of tools that are out there to help make your life easier. One class of tools are cross-platform IDEs and editors, and these run natively on Windows, Linux, and Mac. And a few popular examples include CLine, VS Code, and CppCreator. These tools all provide a graphical interface for command line debuggers like GDB and LLDB, and they can also provide a consistent user experience when you're working across multiple platforms. But they don't necessarily address the issue of having to switch between platforms to debug natively. Another class of solutions is remote debugging, which we can define as debugging a program running on a different system, and likely a different operating system than the one you are working on. One example of this kind of solution are the VS Code remote extensions. And there's actually 3 extensions here. There's the SSH extension for debugging on SSH connections, the WSL extension for debugging on the Windows subsystem for Linux from Windows, and there's the Docker extension. And for more information on these extensions and a demo, I would recommend checking out Julia's talk, which was on Monday. So if you missed that, then you can check the recording. And how these extensions work is essentially you're required to install the backend of Visual Studio Code on your target system that also hosts your source code, build tools, and debugging tools. And then you can debug from whatever host is also running Visual Studio Code. Another option for remote debugging is Visual Studio's remote support, which provides first-class support for GDB and GDB Server. How that works is your source code originates on Windows, and Visual Studio will automatically copy your source files over to your Linux system and maintain 2 synchronous copies of your source tree. So your Linux system only needs to host your build tools and your debugging tools. Visual Studio has native support for WSL, which means that all commands are executed locally and there's no need to establish an SSH connection. And it also allows you to separate the system that you're building on from the system that you are deploying to and debugging on. So for example, you might cross-compile natively on WSL for ARM, and then deploy that executable to a second remote Linux system, an ARM Linux system that's connected over SSH, and debug the executable using GDB server. Finally, both CLion and CppCreator also have remote debugging solutions for debugging against remote Linux systems and WSL. And the last section that I'm going to talk about today is testing. And this is a huge problem area. I'm going to be focusing primarily on unit testing, but I do want to give a nod to static and dynamic analysis tools. And for more information on those spaces, I would recommend these 2 talks. They both occurred yesterday on Tuesday. So again, if you missed them, then you can catch the recordings. All right, so we know that writing unit tests can be difficult, especially if you're working with legacy code. And we also know that they always provide some value, but they can be especially valuable for cross-platform developers because when used in conjunction with a continuous integration system, they can catch runtime errors across multiple platforms. And this partnership is going to be the focus of this section. So what kind of tools are available to help you achieve this? CTest is CMake's test driver program and is used to manage and execute a complete suite of tests with or without a unit testing framework. Unit testing frameworks are used to author individual C++ unit tests, and some popular cross-platform examples include Google Test, Boost Test, and Catch2. Our recommendation is to use CTest and a cross-platform unit testing framework together. Unit testing frameworks provide all of the primitives for designing unit tests, like exception handling and assertions, and when used in conjunction with CTest, can make your life easier than you trying to hand roll all that same functionality on your own. It's pretty easy to enable a CMake project to use CTest and a unit testing framework. It's just a few lines of CMake, and that's something that I'm going to be showing more in my second demo. Finally, for some unit testing frameworks, CMake can automatically extract unit tests at the individual test method level by querying the compiled test executable for available tests. And this translates really nicely if you're using an IDE or a continuous integration system, because it'll allow you to view individual test results at the test method level instead of at the CTest level, which can make it easier to diagnose and find out exactly where things are going wrong. So with that, I can jump on into my second demo. All right, now I'm back in Visual Studio, and the first thing I want to do is show you how I've enabled this project to use CTest and Google Test. So I'll open up my root CMake list, and here I've included CTest, and I've used this built-in build testing option, which defaults to on, to enable testing and add the test subdirectory. Then I'll jump back to the CMake list that defines my test executable. I only have one test executable in this project, but you can have as many as you'd like. And I find and include Google Test. And again, I'm using this vcpkg manifest file to actually acquire gtest. Link against gtest. And then I can use this built-in gtest discover tests command and pass it my box2d test executable. And then CMake will automatically extract unit tests at the individual test method level by querying that compiled box2d test executable for available tests, such that when I open the Test Explorer, I can see individual unit tests enumerated at the test method level. So that means I can run one individual unit test and view the results. Or I can run a group of tests and view the results at the test method level. So in this case, all of the tests passed. We'll also see this same level of granularity in our continuous integration system. So this project has been configured to use GitHub Actions, and I've authored a workflow file that will automatically build this project on both Windows and Linux and run the full suite of tests on push. So to get that workflow started, all we'll need to do is commit our changes. So git commit. The only change that we've made is to add that missing dependency. So I'll add vcpkg.json. We added glad, commit those changes, and then push to the remote. And I did all this using Visual Studio's new Git integration, but obviously you can also use a command-driven workflow as well. So if you prefer command line tools or command-driven workflows, then Visual Studio also now has an integrated terminal so that you can use your command line tools or your command-driven workflows right in the context of Visual Studio. So I'll close this. And there's a couple more things that I want to show you locally before I switch on over to GitHub and walk through that GitHub Actions workflow. So this talk is all about cross-platform development, but so far I've only been building and running locally on Windows. So now I'm going to show you how easy it is to retarget the same CMake project for Linux. So I'll go ahead and make my Linux configuration my active configuration. And I can show you where I've defined that. So here in the CMake settings editor, all I've had to do is specify, it's down here. Make my Linux configuration active and then specify my remote machine name or the build machine that Visual Studio will be targeting. And if I needed to add a new connection, then I could do that in the connection manager where I can add and remove my SSH connections. And I'm targeting a local Hyper-V VM. Here I can also do things like set environment variables, pass CMake variables, pick my compilers and things like that. So now that this configuration is active, when I go and generate the cache, then I will start configuring the CMake project on my remote Linux system. And just to walk through what's happening here, Visual Studio is using all of the build tools that exist on my Linux system. So we're invoking CMake using the CMake that exists on that Linux system. We're going to build with the build tools, in this case GCC and Ninja, that exist on that Linux system. And Visual Studio is automatically maintaining 2 synchronous copies of my source tree on Windows and Linux. So it looks like CMake generation has finished. And now, just like before, I can build and run the samples executable, but this time on Linux. So I'll go ahead and switch over to my VM now so you can see when that application launches. And here I have samples, but running on Linux. I can also debug against an application that's running on Linux. So I'll go into a source file that is part of this samples executable. Control G to go to line 134. I'll set a breakpoint. And this time when I run the samples executable under the debugger, I'm going to hit my breakpoint. And here I've hit my breakpoint and I can step through just like if I was debugging locally on Windows. And this is using Visual Studio with GDB. So it's GDB with the front end of the Visual Studio Debugger. The last thing that I want to do is show you how I configured this debugging session. So I will go to Debug, and Launch Settings for Samples. This option just matches whatever target is active in this dropdown right here. So because I have the samples executable active, then this will bring me to Debug and Launch Settings for Samples. And here I have launch.vs.json, which is where you configure all debugging sessions for CMake projects. So I can do things like pick whether I want to use GDB or GDB server. I can pass arguments. I can set environment variables. So the only change that I needed to make to this default configuration was to export my display variable to match the default or the value of the display environment variable on my Linux system. If you've used remote debugging with Visual Studio before, you might realize that this is a new and streamlined template of type CppCG, and we added that recently to make it easier for you to configure debugging sessions on Linux systems or WSL that use GDB or GDB server. And with that, I'm going to jump on over to GitHub now to walk through that continuous integration workflow that I kicked off. So here we are in GitHub, and here is the run that I started 5 minutes ago. It took 2 minutes to complete. You can see there were 2 jobs I ran on both Windows and Linux, Ubuntu 2004. And I'll jump into the Windows one to show you what was happening. So basically what we did here is we acquire CMake. We acquire vcpkg. We set up our NuGet credentials because, again, I'm using NuGet as the backend for vcpkg binary caching. We skipped the apt-get, update apt, and apt dependencies steps on Windows because they only apply on Linux. There's a few system libraries for OpenGL that I acquired using the System Package Manager. We built with CMake and Ninja, which is the same build tools that I was using locally, and we ran our full suite of tests. So if I jump into this build with CMake and Ninja step, this actually captures both generation and build. So I can scroll down to the generate project files with CMake step and expand it. And here you can see the exact same output that we were seeing locally when I was building on Windows earlier. So here again, you can see the list of 6 dependencies that are being installed, the 4 that I've specified, and the 2 transitive ones that vcpkg is fetching and resolving for me. You can see that again, I'm fetching and restoring 6 packages from NuGet. So I'm using the same binary cache hosted in GitHub packages to download and install these libraries on both my local dev box and in my continuous integration system, so I can be confident that I'm using the exact same version of the library built the same way in both of those contexts. Again, you can also see that this speeds up installation, so this entire operation took 4 seconds. I can also expand this run ctest step, and just like in the test explorer, I can see the results of every single unit test enumerated for me, and that'll make it easy to pick up on what's failing or where I might be having issues. I can then move over to the code tab and jump down to packages. So these are the GitHub packages that are associated with this repository. And again, this is where I'm actually storing my binaries that I'm using for vcpkg binary caching. So you can see I have the x86 Windows triplet of all of the required packages. And I also have the x64 Linux triplet. So everything is hosted here. And then I'll quickly jump back to Visual Studio. The last thing I want to show you in this demo is the actual YAML file that I configured to configure that GitHub Actions workflow that we just stepped through. And this will all be available on GitHub so you can look at it in more detail. But basically it runs on every push, and then every step that we saw corresponds to a few lines of code here. So which operating systems do I want to run on? Acquiring vcpkg and CMake. I'm using some actions that make that step a bit easier for me. Setting up NuGet credentials, acquiring dependencies, building, and then running the suite of tests. So that was a quick run through, and you can look at that in more detail if you want. And with that, I will hop back on over to my slides. All right, just to quickly recap what we showed in this second demo. We showed how easy it can be to enable a CMake project to use both CTest and Google Test. It's just a few lines of CMake. We showcased remote debugging on Linux with Visual Studio, and that was using GDB and the front end of the Visual Studio debugger. And I could set breakpoints and step through my code just like I was debugging on Windows. We also showcased a GitHub Actions pipeline with GitHub packages. So there we acquired CMake and vcpkg. We downloaded cache binaries from GitHub packages. We configured and built our CMake project on both Windows and Linux agents and ran our full suite of tests. In my demo, all of my tests were passing, but if they weren't, we recently added the ability to debug Linux core dumps in Visual Studio and the latest release of Visual Studio, which was released on Monday. And those core dumps can be hosted on either a remote Linux system or WSL and leverage our remote debugging capabilities. And this might be especially helpful for you if you run a Windows shop, so you primarily build and debug locally on Windows, but you also deploy to Linux servers, and you want to diagnose crashes, whether they occurred in your continuous integration system or on those servers in a familiar environment. There was a demo of this functionality in Marion and Sai's talk, which was on Monday. So again, if you missed that, then be sure to catch the recording. I also just published a new blog post that walks through this feature and describes it in a bit more detail to the C++ team blog. And in general, our team blog is a great place to go to stay up to date with new functionality, or also just to see descriptions of new workflows. With that, I hope that you enjoyed this talk and that you maybe gained some awareness of all the tools that are available to help make your cross-platform development workflows easier. I hope you realize that while you might have some problems that are completely unique to you and your team, you also might have some problems that are shared between other cross-platform developers. And for those problems, we can use shared solutions. And finally, I hope you will talk to me, talk to others on my team, talk to other people who work on tooling, because we work on tooling because we hope it'll make your lives easier. So if you have unmet needs or you have particularly painful parts of your workflow, then please talk to us, because those problems are probably not specific to just you. They might be shared with others, and we're constantly iterating over our tools or designing new tools that we think will help make your lives even easier. As promised, so I was working with a private fork of this repo today because the GitHub packages are private, but I also have everything checked into a public repo. So if you want to take a look at that and take a closer look at anything, including the YAML file that we use to actually configure that GitHub Actions workflow, then you can take a look at that. And this is the URL. Please enjoy the rest of the conference. And again, if you have any follow-up questions, comments, or just want to say hi, then you can stop by our table at the virtual expo hall. These sessions already passed. There's a couple that I called out in my talk today, and there's a few more that are still coming. And these are talks given by other folks on Microsoft's C++ team. So it looks like there's one more today and one on Friday. So thank you again for coming. Hi, everyone. Hopefully you can hear me all right. Just post in the chat if you can't. And I'm now going to go through some of the questions that were posted throughout the talk. So starting with this first one. Sorry, just looking at the chat. So starting with the one with the most upvotes here, do package managers pull and build dependencies locally or grab pre-built binaries from some well-known location? That's a great question. So I first want to say that different package managers support different functionality. I will speak to vcpkg, which is the tool that I demoed in the first demo. So with vcpkg, it's not pre-built binaries. It is by libraries that you have built and compiled at some point locally with your own build tools that you know integrates well with your own projects. You can then you modify your VC package installation to use binary caching. And you can do that by setting a few environment variables. But in that way, you can cache those binaries that you have built locally in some shared location. So that can be GitHub packages like I was using, or a file share. And then other developers working on other systems will be able to pull down those cache binaries that you have personally built to use on their own systems. So it's not pre-built. It's something that some developer on your team has built intentionally. And by default, if you don't enable binary caching to point to some remote shared cache or a file share or something, then binary caching is done locally so that you on your own system will always use this. You'll never have to build the same library twice the same way. And if you have more questions about that, you can come to our booth, talk to me, or talk to some of the folks who work on VC package. Second question, will there be Catch 2 support for Visual Studio? That's not something that we have a firm timeline to share right now. In the chat, I did post a link to a developer community suggestion asking for that. So please go ahead and upvote that. We use your upvotes to help prioritize new features. And I believe there's also a open source third-party extension that provides some Catch 2 support. So I can't speak to exactly what that provides and how it integrates with Visual Studio, but it might be something that's worth checking out. All right, next question. Let's say your app depends on package A, but package A depends on package B. I have a bug in my app that's traced to package B. What are effective ways to prototype and test the fix for package B? That's another great question. When you're working with VC package, some ideas that come to mind is that you could fork VC package and point B to your own fork of B, or somehow modify CMake to use your own local copy of B that you know works. But I think this would still be a bit of a pain. And so Robert, who works on VC package, is going to be at the Microsoft booth today at 1:30 p.m. Mountain Time. So I would probably defer to him for some more information on strategies to test that dependency. All right, up next, is VC package appropriate for programs using multiple languages? So for example, C and C++, Rust, Fortran. So VC package only supports C and C++ right now, but it is open source. And so you could potentially hack something together that works for your own needs, but officially it supports C and C++. Does VC package support iOS and Android triplets at this point in time? My answer to that is I don't think so, but I can follow up and share look through the documentation. I think it's just different variants of Windows, Linux, and Mac. But again, I will defer to the booth, and I can also follow up and look that one up pretty easily. I just don't know off the top of my head. Can we call CMake from C++ source code? So generally, no, you can generate C++ code from CMake, and I guess that your tests or binaries could call CMake, but I don't think you would want to do that. So generally, no, CMake is the build script, and so it's how you define your build, and it's not something that you really invoke from your C++ source code as far as I'm aware. And if someone has more information to share on that, please go ahead and share it. Why must a non-system, non-build tool dependency tool be language specific? Is cross-platform, Nix, GUIX not possible? So I don't have a ton of familiarity. I'm not very familiar with those tools. I can say that C++ has a lot of requirements to maintain ABI. It has its own set of requirements as opposed to something like C# or other languages. And so as for the specifics that you run up against when building a package management solution for C++ that is not satisfied by existing tools, I guess I would again defer to people who work on VC package for a more specific answer. Presents its own whole host of problems that are language specific. Okay, I want to teach students C on Unix with Visual Studio. Is that possible to build and debug a cross-platform C file without a CMake project? So yes, it is possible. We do have MS Build-based support for Linux applications that build and are debugged natively on Linux. So if you check out our documentation, I can post a link to that after this talk. You can get more information, but it's basically just like a console application, or just like you were working with MS Build on Windows, except for everything is invoked on the remote system. So very similar to CMake. Is the goal to make CMake project have parity with solution and CXProj? If I recall, last time I checked, CMake didn't have support for profiling. So yes, that is our long-term vision. So with things like the language services or things like that, or project manipulation support, we are trying to get closer to what you're able to do via property pages in a MS Build-based project where Visual Studio helps you to manage that underlying build system for you. And so, yes, we know that there are still some parity gaps. We think we're getting pretty close. I know that there exists a developer community suggestion for profiling specifically. So I would give the same advice that please go ahead and upvote that, because we do use your upvotes and your suggestions to help prioritize what we work on when it comes to new functionality that we're adding to the product. But we do want you to be able to use CMake in the same way with the same requirements as if you were using MS Build. Can you recommend something for migrating from a Make to CMake build flow? That's a great question, and something that I have been hearing. We don't provide any documentation or any kind of automatic help there. So I guess I don't really have anything off the top of my head, but I would love to open it up to others in this talk who are doing cross-platform development to see if they have tools that they're using that I can learn from and also help share with the rest of the community, because that's a great question and is a big pain point of migrating to CMake. Are there other build system generators integrated by Visual Studio? So not natively, other than MS Build, CMake is the only build system generator that we have first class support for, but there is something called open folder mode in Visual Studio, which is quite similar to how VS Code works, if you're familiar with that product at all, where you have your own JSON file where you configure the build step. And so you can kind of work with that to hook up your own custom build commands, but we don't have first class support for anything other than the CMake support that I showed, and then obviously MS Build as well. Will there be a debugger for CMake files? I don't have anything firm to share, but that is something that we have been playing around with. Is vcpkg planning any public binary caching a la Conan Center? As far as I know, that's not in the immediate roadmap, but we're investing a lot in vcpkg. So again, I would defer to Augustin and Robert, who kind of are driving the vcpkg experience, who can speak more to our timeline. I can also post in the chat we have a public backlog. Or feature roadmap, I guess is the better term, of what we're working on in vcpkg. So it's not currently part of that, but you can see what else is coming soon. I know some of the things that we have publicly committed to are better integration in Visual Studio and VS Code. So kind of a UI to help you manage your libraries, install new libraries, and things like that. And then the things I talked about in the demo as well, like versioning support and registry support. All right. It looks like we're almost out of time, and I answered most of the questions. So sorry if I didn't have any specific answers. I would again point you to the Microsoft booth, or you can reach out to me on Twitter also, and I can help get you in touch with someone who can fully answer your question. I'll jump back over to the chat. Thanks. Oh, I see Augustin works on vcpkg, so anything from him should be helpful and to address some of these questions as well. Yeah, I think that is all the questions. So feel free to reach out on Twitter or come to our booth. Thanks everyone for tuning in today.